Okay, good morning everyone. My name is Marcelo Castro and I'm going to present model transformation for smart grid applications. This presentation was done for MODPROD 2022 and it basically consists of an introduction where we talk a little bit about the motivation, previous efforts and goals, the methodology behind it, the results, and some final considerations. First of all, we need to think about the future energy scenario where a large number of renewable energy sources are going to be deployed into the grid together with many different power electronic devices. And of course, the grid will become more and more interconnected. And this new grid will actually require for new modeling and simulation techniques and tools to be developed and tested, right? And this is because we need to properly study these clean technologies, and also we need to be able to share models more easily. But this is way different from what we have right now in today's scenario. For example, what we have right now is that utilities models are bound to a few specific proprietary tools, such as PSSE, for example. We have a lack of interoperability, which means that the models that we share are basically just a collection of parameters instead of a description of the model itself, like equations and things like that. And also, because we are just sharing the parameters, and because one model is actually used to many softwares to be studied in many softwares, we actually need to duplicate and re-implement every time the same model over and over again, which leads to inconsistency and errors due to those duplications. Well, one solution to actually address this problem is the model transformation tools, which are basically computer programs that take a model as an input, which is called source model, and it produces a model as an output, which is going to be called target model, right? And there are many benefits of this kind of automatic translation tools, such as, for example, you're going to need only one model, and depending on the application that you want, you can use your transformation to create that specific model. And also automatic translations, they actually avoid common mistakes that are made when you're trying to re-implement or duplicate a model. Okay, so they're more consistent. And of course, there are many previous efforts towards those model transformation tools in power systems. For example, sim to mod, which is a model to model transformation. We also have the simverter. You can also find this kind of things outside the power community, of course. Beam to Modelica. You can also find Dito, which is also a kind of a transformation tool. So many tools in the literature, but our solution, our proposition is that open source. It's based on open source and open standards for interoperable models. So our model transformation tool solution will actually take, for example, PSSE model as a source or SIM as a source, and then it would output a Modelica model using the OpenAPSL, which OpenAPSL stands for Open Instance Power System Library. And why we are choosing Modelica as a target model? Well, because first of all, it's equation based, which means that model, when we share that model, we are actually sharing the equations that compose that model, right? We actually are sharing the mathematical representation of the differential and algebraic equations that compose the dynamic of that model. In addition to that, Modelica is an open source, open access standard language, which means that we can actually create a Modelica model and simulate it wherever we want, Modelica compliant tool, right? So you are not locked into one solution only. For example, you can simulate it you might be able to simulate it in many different Modelica compliant softwares. In addition to that, Modelica is compliant with the FMI standard, which means that we are increasing the interoperability of that model, because the Modelica model can be exported into an FMU, and that FMU can be loaded into many other different tools which are com compatible with the FMI standard. And the OpenAPSL library that we are going to use here is a Modelica-based library for power system dynamic models, and it has been developed. It's been in development since for several years right now, and so it's very robust. And the scope of the transformation tools that we are going to show here are basically two. We're going to show a PSSE to Modelica transformation based on templates, and a Sim to Modelica transformation tool based on XSLT. First of all, in order to guarantee that our translation will be actually valid, we need to, first of all, map a model from PSSE or from Sim into its Modelica representation using OpenIPSL. And to guarantee that actually both models are representing the same dynamic behavior, we need to create automatic tests to verify those models against PSSE. In addition to that, we need to integrate that testing routine into a much more bigger and robust routine where every modification that you do to one of the models, it's going to be tested and all the results are going to be assessed to be sure that even with that small modification that you just did, the results are not compromised. So you're still valid. So your transformation will be still valid. Okay. One example of this validation test is here. We simulate a very small system. Basically, we are trying to assess one component per time. And here, in this case, we are trying to assess this GenSci generator model. Okay, it's a generator model with a salient pole and exponential excitation. Okay, and here we are trying to assess the rotor angle result to be sure that the rotor angle will be actually the same in Modelica and in PSSE. So in your left, you're going to have an example of a failed verification. So it means that the OpenAPSL result here, the model was not well implemented. But on the right, you can see a successful example where the result actually matches the base result, the result from PSSE. And the tolerance that we use here in all the verifications is 1%. So it's just 1% tolerance, okay? After that, we also need to assess the model's portability because we chose Modelica, saying that Modelica will allow us to be more interoperable, right? We would increase interoperability by using Modelica. And here, we're going to load a model into OM edit, so open Modelica, simulate that model, and then compare that result with the other different tools that are Modelica compliant, for example, Model on Impact, Timela, System Modeler, and they all gave us the same result, which means that that library, the models that we composed with that library, they can actually be loaded into many different Modelica compliant tools, simulated there, and their results will be still consistent. In addition to that, we can take models that are created with OpenAPSL and export them through the FMI standard. But therefore, we are exporting them as FMUs and load them in, for example, Simulink, Python libraries such as FMPy, PyFMU, or real-time simulators, as you can see in this picture. And once again, even when you simulate it in a real time, you're going to get the same result, which means that that model is consistent and interoperability is verified. Now, for the transformation tool design and the implementation, we're going to give a brief summary. The first transformation tool is the Sim to Modelica. Okay, so this Sim to Modelica tool uses an XSLT engine. So XSLT stands for Extensible Style Sheet Language Transformation. And basically this XSLT is composed of a translation rules that are going to be used by the engine together with XML files to generate another file. Okay, so basically we have an engine, an XSLT engine that takes the translation rules and the inputs and creates the .mo file, which means that it creates a single file, a single Modelica file that will contain the entire system, the entire power system that we are translating. And the XML files that are used as inputs are actually basically the SIM files. So SIM files are actually created using SIM stands for Common Information Model, and they're created using extensible markup languages, XML. And they are actually composed of multiple files, including state variables, dynamics, equipments, topology, steady state hypothesis. So the full description of that network is described in those XML files. Those XML files will be inputted into the engine together with the translation rules, the XSLT file, the translation rules that we created, and the engine will actually create this Modelica file automatically. This engine is normally locked into a specific tool, but we are assessing right now how to actually lock it in a Python environment so we can integrate it into the next tool that we are going to talk about, which is the PSSE to Modelica. In this case here, we use a different approach. So we use parsers, readers, and writers. So a .raw and a .dyr file are used as inputs here. And we use parsers to actually dissect the information, separate that information, categorize that information. And by using mapping rules that were created in order to associate a PSSE model, or at least a PSSE file, a PSSE representation of the model to the actual Modelica model, we use that mapping rule, which is hard-coded in a Python script. And that Python script and that transformation tool will actually generate for us a package. And this package will contain many files such as the grid.mo, a pf.mo, and plants.mo. And the grid.mo is basically a direct translation of the raw file, which includes the lines, buses, shunts, loads. So basically the structure of the network. We're also going to get from the raw the power flow results, which are used to start our model dynamically. And the DYR file will be used to actually generate the substations that contains machines or dynamic devices that we actually need to analyze, that we actually need dynamic models to represent them, such as machines, exciters, turbine governors. And then this output, this big output, this package output would actually be the grid that you load into a Modelica compliant software to simulate. Okay, so in order to assess that the tool that we created, we first want to see if the translation from the SIM to Modelica and from the PSSE to Modelica tool will actually be consistent between themselves, right? And the base result. And also we want to test, especially the PSSE to Modelica tool, we want to test it in many different power system models in order to assess the performance of the tool, right, when translating. So here we translated the IEEE 14 bus, and as you can see, the PSSE base result, the PSSE to Modelica translation, and the SIM to Modelica translation, they all have the same result. They all gave us the same result, which means that the translation is consistent. It doesn't matter the strategy that is used, it is consistent, and they gave us the same result. So the models that we are using are consistent with the base, with the source model, okay? In addition to that, we assess the PSSE to Modelica performance. So we use that transformation tool in 3 different machines. So one is a Linux-based, one is a Mac-based, and the other one is a Windows-based. And the goal here is not to compare the machines, but to assess the tool scalability independently of the operating system that we are using. And to do so, we actually tested 7 different systems that goes from 7 buses to 684 buses, from 5 machines to 234 machines, from 1,000 DAs to 63,000 DAs. And this increasing complexity means that we are transforming toy examples and also entire grids, okay, such as the Icelandic system, which represents the entire Icelandic power system. And as you can see here from the performance results, the total time that was spent to translate those models, even the largest one was less than 3 seconds. Okay, in the slowest configuration, which in this case is the Mac, it took less than 3 seconds for the translation to be done. And if we project this result to more than 2,000 buses, even the slowest configuration would actually take less than 2 minutes, actually less than 3 minutes to translate a full 2,000 bus system, okay? Which actually shows that our tool is in fact scalable. So in order to conclude, to propose some final remarks on this presentation, we need to remind that the mapping between the SIM or PSSE to Modelica is possible. So it allowed the models from one tool to be translated into another tool without any loss of information, without any loss of dynamic behavior to be represented. We also need to talk that the library in Modelica, the Modelica library, is compatible with many Modelica compliant tools, but also is perfect for FMI, for the FMI standards. So you can actually export those models using FMU and simulate those models in different another hardware or other software such as Simulink or real-time simulator. And we also could assess that both translation strategies are shown to be effective because the results were actually consistent between each other and the base result. And also the PSSE to Modelica was shown to be scalable for larger models and complex grids which actually represent real systems. For example, 2,000 buses was expected, like the translation of 2,000 buses is expected to take a couple minutes, right? But of course, there's still room for improvement. We're still assessing how to simulate big systems, the very large systems in Modelica. And these for sure are the next steps for this project. We also would like to acknowledge the New York Power Authority contributors such as George, Raul, and Benham, and also external contributors such as Dietmar Winkler and Svein Harald Olsen. And all these results are actually available in this public website where you can check a little bit about the overview of the project, the curves and the reports from the model validation, a little bit of the tool description, so how to use the tool and information about the tool itself, and some contact information so you can reach us out. Well, thank you, and that's it.